Okay, so what we're going to do today and Monday is talk about area between curves, and then we're going to talk about volume. Okay, throughout this entire unit, you could call this unit applications of integration. Okay, we have the applications of differentiation. Here's our applications of integration. Okay, there are a lot more applications of integration, but you would learn those in calculus too. Okay, this is actually a couple of these topics when you go to Calc 2 will be a part of the class. Okay, but this is in Calc 1 for our AP course. Okay, so here we go. First of all, do we know how to find the area under a curve?
Yes.
Yes. And how do we do that?
Integral.
Okay, our integral, okay, our integral from a to b, right, of f of x dx is just calculating the area between a curve and the x-axis, right? Okay. Well, now I want to find the area between two curves. Okay? Any ideas on how we're going to do that?
You take the area of one and subtract the
Basically what's going to happen. Take the area of one, subtract it from the area of another. But we need to be careful in which order we do our subtraction.
I guess we'll take the bigger one.
Yes. Okay? So in order to find the area between two curves, we are going to subtract the area under the lower curve from the area under the upper curve. Okay, we will always get positive area when we talk about the area between curves. We had negative area in our last unit because that represented area underneath of the x-axis. Okay, when we are talking about area between two curves, that's always going to be represented with a positive number. So you are going to take the area of your bigger or your taller function and you're going to subtract out the area of your lower function. Yes?
Would it matter as long as you make it positive at the end if it's like absolute value?
Well,
Because it's something to play if I get
right.
a curve like across and you might not know which is which. Whichever one's bigger.
Well, we are going to know which one's bigger.
Okay.
Okay, we will be sure to set it up that way. All right, I want you to look at this picture, okay? If we find the area under this curve, then we're finding all of this red area, correct? If we find the area under this curve, we're finding all of this green area, okay? So when we take the red and subtract out that green, we're finding just that blue area, the area in between the two. Yes?
Say if you don't have a picture and your area comes up to negative, you're looking for the biggest negative number or closest to zero?
You will always have a picture because if there is not one, you will draw one.
Okay.
Okay? Here is where our knowledge of functions is going to be very important because we're going to need our pictures. Okay, now sometimes we'll have a calculator, sometimes we won't. Today we're going to work without a calculator. Monday we'll work with a calculator where the problems get a little bit harder, okay? So, we will always have a picture, and you will always draw me a rectangle representing the height of the rectangles in your book. Okay. Let me go back to here. Okay. Each of these rectangles, okay, an integral is summing up an infinite number of infinitely small rectangles. How wide were these rectangles? Delta x, right? And we summed all of them up. So we're going to draw a rectangle so we know the height of our rectangle. We know where the top is, we know where the bottom is, okay? Okay. So find the area of the region bounded by y equals x plus 6, y equals x squared, x equals 0, and x equals 2. Okay, so first of all, we need to draw our region correctly. Okay.
So x equals 0 and x equals 2, the interval.
What?
X equals 0 and x equals 2, the interval.
It kind of looks like that's what could happen, right?
So what's the term?
You will not always get an interval. It's going to be where you have intersection points.
Oh,
Okay.
I'm with you.
Okay, so y equals x plus 6. What does that look like?
So line starting at 0, 6, and it's going to slope to 1.
Okay. Y equals x squared.
That's just
So 0, 0, 1, 1,
negative 1, 1, 2, 4, negative 2, 4,
3.
9, negative 3, 9.
And that's 11 years.
Oh, cool. Okay. And x equals 0. Looks like what?
Right on the x or y axis. Straight line. Vertical.
And x equals 2. Okay. So in green, I know this is really quickly, I'm very sorry. Here is our region that we're finding the area of. Right? What? Oh. So what I'm going to do is I'm going to draw in a little rectangle to represent, well, I have an infinite number of these rectangles that we're adding up with our integral, right? Okay, so what are our boundaries? We begin at
0,
0 and we stop at x is
2.
2. So we have the integral from 0 to 2 of our upper function is
Y plus 6. Or x plus 6.
x plus 6. Subtract our lower function, x squared.
So,
Yes.
So if they like intersected before too, you'd still take it. So like say the parabola went up and intersected before too, you'd still take this area over here, right?
Yes, and we'll talk about what we would have to do in that case. Okay. Okay. All right, so from here, not a problem, right? Antiderivative of x,
X squared.
6,
6x.
x squared
1/3 x squared.
from 0 to 2. Wow,
Whoa. He did that in his head.
I know. And you're all impressed.
Wait.
Okay.
What did you do?
How did what?
Plus 4 Oh. Wow.
Okay, now, okay, I'll get to your question here in a couple of examples, okay? Jared's question was, what happens if we're trying to find, like, from 0 to, like, 6? What happens because we have this intersection right here? So, we'll get there in a little bit. Let's try another one. Here's where the boundaries are not clear. Here's where a picture is very important. Okay? I want the area of the region enclosed by y equals x squared and y equals 2x. Okay? So y equals x squared is a parabola, right? Here's my parabola. Y equals 2x. What are the coordinates for y equals 2x? We have our 0, 0, 1, 2, 2, 4. Oh. It's a really bad line. Now, let's say you weren't certain where these intersected. How could you algebraically find it? Okay, you would have to set them equal to each other. Where does 2x equal x squared? Okay, and
0.
0. Okay, so here is what our little rectangles look like with thickness dx. Okay, to find the area.
Where do you draw those rectangles if we don't use them?
Be patient.
Oh no, we're gonna be doing that sometime.
No.
How did you draw that?
I drew this in so we knew that this had thickness dx.
Okay.
Okay,
So
you
dx
will
is the
see
green.
why here in a little bit.
Okay.
dx is the green. Right.
Mhm. So our boundaries are from 0 to 2 because that's where these two curves intersect. Okay. If we look at our rectangle, our top function is the blue, which is minus our bottom function. Okay. Now, we can go through the integration, but that will be just fine, right? Okay. I'll let you practice the integration in your homework. Now, if you are solving for these intersection points algebraically, how do you solve an equation like this?
You could divide out the x.
No, you can't divide out the x.
You get x equals 2, and that's the x.
Set it to 0 and factor.
Right.
Okay. Now, I know that that is one that you're like, I don't need to do algebra with because the graph gives it to me. But just for future references, when our problem gets a little bit more difficult. Okay. Don't say that. It's going to be just fine.
Alright. I'm sorry.
X equals y squared. What does that look like?
Can we change it to y
Square
equals
is
square root of
x.
x? Are we allowed to change it to a square root function? Like we can.
Well, be careful. It is not just y equals the square root of x.
That's why it goes plus or minus square root of x. Ah.
So you have it is a sideways parabola, right?
Yeah.
Can you do antiderivatives of non-functions?
Well, we need it to be in terms of x. So we need square root of x and negative square root of x. So we have two functions drawn.
Oh.
You see what I'm saying?
Okay.
And y equals x minus 2 would look like this.
So we're basically.
Right.
So you split them up into basically two separate functions.
Yes.
Okay.
Okay. So the area we want is this green area right here. Okay. Where do we intersect? 4, 2, and how about positive 1, negative 1? Right? But we need to go from 0 to 4. Now, what's the problem? Can I just go from 0 to 4? Why?
Because you have parts of the graph that are on
That's not a problem.
Because you can't play that because it's negative like it's not a function.
We have three functions up here.
Oh.
Because you haven't drawn a rectangle yet.
Okay, well, let me draw a rectangle.
Although it makes sense.
What's
You have to
these?
do three different. You have to use geometry.
No.
Like
Use
you
the
can't-
line.
you can't
Line
subtract
for the-
one, you have to use
What's the difference between those two rectangles?
They're connected to different.
Okay, the function on top always stays the same, but our function on bottom changes. Do you see that? So we need to actually find two different areas. We need to find the area from 0 to 1, and then the area from 1 to 4, because the function that is the lower function changes. Okay?
the area from
So here we have the integral from 0 to 1 of positive radical x minus negative radical x. Okay? And then we would have to add this region. So the integral from 1 to 4, our top function is still radical x, but now our bottom function is x minus 2. Make sure x minus 2 gets subtracted in parentheses. Okay.
So that area that's below the x-axis is still positive.
Yes.
Well, we're subtracting negative area, so it makes it positive. Right? Okay. Now, here's where some people get into some problems. We're subtracting the function x minus 2. So when you go to actually do this integration, okay, you have square root of x minus x plus 2. Right? Well, I guess we can just change this to, whoops, 2 radical x. Okay? Now, I am not going to go through the integration all the time with these problems because you know how to do the fundamental theorem calculus, you know how to integrate, okay? What I'm worried about is how to set up these problems, and since today we get 5 minutes cut off of class, I'm going to save some time and not do this, okay? But if you would like to go back later, this is 9/2, okay? Okay. Now, we can do this in a simpler way.
Why didn't we always teach us a simpler way after the hard way?
So you know how it works.
Oh, okay, that makes sense.
Because you know how to.
Yeah.
The beauty of math is, in some cases, there's more than one way to do a problem, right? In this case, there's more than one way to do the problem. Now, one is easier than the other. However, you don't know the next one. You don't know the easier way. Okay? I've been making you draw the rectangles. Why?
So
Okay.
you know
It's a height.
yeah,
Okay, we know the thickness of our rectangle.
But doesn't that thing change?
Yes, they change, but the function that gives it the height and the function that gives it the lower height, those don't change. Okay? Now, it is possible to draw our rectangles horizontally so that we have thickness dy. And we can take the integral with respect to y to find our area. Okay? So here, we can find the area by taking the area of the right function, the biggest, and subtracting out the area of the left function, the lower function, okay? And we can find the area with respect to y. This means we would need all of our functions or all of our equations to be in terms of y instead of x. Okay? So, how does that change our last problem?
Y squared.
Okay? We have this, correct? Not a very good graph, I apologize. But notice that when I draw in a horizontal rectangle, the function on my right never changes. The function on the left, the equation, it's not a function, I apologize, but the graph to the left never changes, right? Our left graph is y squared. Our right graph is y plus 2. So to find the area here, we have the integral from, now we have to use our y limits. Y is -1 to y is 2. Our right function is y plus 2 minus our left function is y squared. No, because if we solve for x, we get y plus 2. Is that what you're asking?
I see. Yeah, got it.
Okay, so now we can do this area with only one integral, right? Less work? Yay. Okay.
So does this only make some easier?
Yeah.
Well, yeah, this was easier because we had consistency with our right and left function. Whereas over here, our bottom function changed, so we had to do 2 integrals. Now, like this one, it would be the same amount of work, right? This one, we would have to do a couple integrals if we wanted to do it with respect to y. Now, what it's not going to make easier is if solving for x is messy, right, to get our function in terms of y, then it's not beneficial. Sometimes we're going to get graphs where having them in terms of y is easier, okay? Like if, like that sideways parabola, right? Your homework. I know, it's almost time to go. Can you believe it? Okay. So I believe in your homework it tells you when to do it with x, when to do it with y. Okay. Please make sure you do this homework this weekend. Okay. I will tell you, if you do not practice in this chapter, the test is going to be a disaster for you. Okay. You have to kick the senioritis out the door for this class.
Yeah, Jerry.
Okay. Or the junioritis, whatever you may have.
Or the sophomore.